Hello everyone. In this session, I'd like to explain the molecules and the condensed matters. First topic is the types of molecular bonds. Second topic is the molecular spectra. Third topic is the structure of solids. Fourth topic is the energy bands. Last topic is the free electron model of metals. First topic is the types of molecular bonds. So molecular bonds is an interaction that holds atoms together to form a stable structure of a molecules. First bond is the ionic bonds. This bond is related to the interaction between the oppositely charged ionized atoms. Two atoms separately are located in the different positions. First of all, we remove an electron from a sodium and add it to the chlorines. So we need the energy of the 1.5 electron volt to remove the electron from the sodium atoms. Then release the energy to connect the sodium ion to the chlorine ions. So positive charged sodium ions is bounded with negative charged chlorine ions. Then energy is released. Amount of the released energy is 5.7 electron volt. The net energy is obtained 5.7 minus 1.5 electron volt. It becomes 4.2 electron volt. So this is the energy released by the formation of the ionic bond. Second type of the bond is the covalent bonds. So in the last case, the sodium is easily lose electrons and the chlorine captured lost electron from the sodiums. But if we consider the two identical atoms, like hydrogen atoms, so hydrogen atoms is separately located. Then two separate stable atoms exist. The two separate atoms get close together. Then electron cloud becomes overlap. If the two electrons have the opposite spins, then electron charge clouds with the opposite spins are concentrated in the regions between the two protons. Electron charge clouds are concentrated in these regions. This electron cloud actually attracts the two protons to form the hydrogen molecules. So we call such a bond is a covalent bond. Also, we have the type of the bond, van der Waals bonds, the interaction between the electric dipole moment of molecules, dipole-dipole interaction. For example, if you consider the water molecules, O and 2H, H is preferred to have a negative charge. So the separation of the charge occurred inside of the molecules. So we call it this is dipole moment. So this dipole moment interact. So this is a van der Waals bond. Also I explained positive charge is located in the protons. Then negative charge of the O is bounded with the positively charged protons, H. So this bond is a hydrogen bond. The last one is a metallic bond. Positively charged ion is located inside the metal, and some electron is detached, and it could freely moving inside of the metal. These electrons form positive ions together. This is a metallic bond. A molecule has a different spectra from an atomic spectra due to the rotational motions as well as the vibrations of atoms in molecules. This is a diatomic molecules. This molecule, for example, H, hydrogen molecule. This molecule is making a circular motion. For example, this molecule, circular motion. This is a rotation energies. And also these molecules is connected with the springs. So sometimes the separation becomes longer or shorter. This kind of the oscillational motion is happening. when we consider the molecules, we need to consider the rotation motions and the vibration motion of the atoms inside a molecule. The first one is the rotation energy levels. So we consider diatomic molecules. Atoms with the m sub 1 and m sub 2 are bounded together to form a diatomic molecules. Then this molecule is making a circular motions. M sub 1 and M sub 2, making a circular motion around the center of mass. The moment of inertia can be calculated with the I equal M sub 1 R sub 1 squares plus M sub 2 R sub 2 squares. This is center of mass. Then if you use a reduced mass, moment of inertia can be expressed M sub R reduced mass times the distance between the two atoms, R sub 0 squares. The angular momentums is quantized angular momentums is L square is L times L plus 1 h bar squares. With the rotational energy, L square over 2I. Then you can substitute this L square to find out the rotational energy. Is expressed E sub L is L times L plus 1 h bar square over 2I. For the L is an integer. You can substitute the integers. If you substitute the L equals 0, energy, rotation energy becomes 0. This is corresponds to L equals. If you substitute L equals 1, so this part becomes a 2 h bar squares over 2I. So if you substitute L equals 2, it becomes 2 times 3. So this becomes 6 h bar square over 2I. This is rotation energy of diatomic molecules. And also we need to consider vibration energies because the two atoms is bounded together and making oscillational motions. Diatomic molecule is modeled as 2-point masses connected by springs. Harmonic oscillators we use to model the diatomic molecules. So M sub 2 is making the vibrational motions around the equilibrium point. The energy we have already discovered. The energy of the harmonic oscillators is E sub n is n plus 1 over 2. This corresponds to the 0-point energy h bar omegas. So even if you substitute n equals 0, it's not a 0 energies. So 0-point energy n equals 0. Distance between the two energies is h bar omega. Same h bar omega. h bar omega. So vibrational energy is expressed n plus 1 over 2 h bar omega. In a real situation, this rotation and vibration energy is combined. So energy of a molecule is expressed. Rotation and vibration energy is L times L plus 1 times h bar square over 2I plus n plus 1 over 2 h bar omega. For each n, there are many L, forming a series of closely spaced levels. So here, if you consider that take n equal 1, this from the vibration energy, you can find the different L. This comes from the rotation. Take L equals 0. This exactly equals the vibration energies. If you substitute L equals 1, because of the rotation energies, energy of the molecule is increased. N equals 2, L equals 3, so you can find. Also, each n equals 2, different vibration energy, we can obtain. Higher vibration energy, we can obtain. For n equals 2, we have another rotation energy. We have a series of the closely spaced energy levels. This is the end of this session.